Hello, everyone, and welcome to our newest virtual Chase the Knowledge event. As Sherry mentioned, my name is Jason Merkel, and I'm the technical manager for Chase Plastics. We put together the Chase the Knowledge platform a few years ago as a way to help educate our customers on the various aspects of the plastics world. Traditionally, we've given these presentations in person, but given that 2020 has been a bit of an oddity, as you're all aware, we're happy to present to you virtually today. At Chase, we strive to be a materials and processing consultant as much as a resin distribution company. Our team of technical development engineers is standing by to help you with any of your product selection, design, testing, or troubleshooting needs. We come from a variety of technical plastic backgrounds and levels of experience, and we welcome the opportunity to provide insight on any of your projects or problems, whether they be large or small. I hope you find this presentation helpful in understanding the process we go through when helping to choose the right polymer for an application. And we'll be sure to follow up with other Chase the Knowledge events in the future on other technical topics. Speaking of which, our next Chase the Knowledge is already scheduled for next year. We will be presenting on the different types of thermoplastic elastomers and the advantages of each. You can see here that is noted for Wednesday, February 10th. 2021, again from 2 to 3 p.m. Eastern, and we hope you're all available to join. Same registration process as you went through for this one. You can go to our website to register for that, at chaseplastics.com/webinars. Also on our website, you'll be able to find our previously recorded webinars and all future webinars that we're recording as we're recording this session right now. Again, that website is chaseplastics.com/webinars, where we have several topics listed, including understanding plastics data sheets that was presented earlier this year, as well as drying polymers, families of polymers, polymer modification, and polymer structure. Without further ado, I'd like to introduce our presenter, Andrea Kendrick, who is a technical development engineer for Chase Plastics. Andrea is based here at our Clarkston, Michigan headquarters and supports several regions with technical service and application development. Andrea has her bachelor's degree in plastics engineering and technology from Ferris State University, and she's been with us here at Chase for 5 years. Andrea, take it away.
Good afternoon / good morning, everyone. I'm glad you guys are able to join. We'll go ahead and get started on the 5 fundamental steps of material selection. So our agenda for today, we're going to talk about the importance of material selection, kind of the why behind why we do it. We're going to go over some polymer chemistry information. This is kind of what I would consider maybe the building blocks of, why and how we help make decisions for what material we're going to use, what application, stuff of that nature. Then we're going to go over the process of material selection. This is where we kind of talk about the 5 steps that you'll want to take when you're looking at an application and how you're going to start to select material for said application. And then we have a couple product examples that kind of walk through the different steps that we would take as a nice overview of kind of what that looks like when you're doing it. So the importance of material selection, why do it? Chase Plastics, us alone as a distributor, we represent over 26,000 grades of material, meaning we have a lot of material to offer, and that's just at Chase alone. That doesn't include other distributors, other manufacturers of material. So there's so many options available that it can be quite overwhelming if you just start throwing things at a board and hope to just pick the right material. So what we want to do is we want to start to ask the right questions. We want to understand, what are your requirements? What do you need in this application? Those then will start helping us narrow down the different types of material families that we would be able to use in that type of application that isn't going to maybe fail or not meet one of your requirements. And so as we kind of get into this a little bit, I do want to keep, the note out there that sometimes as maybe molders or material people that are selecting materials, you might find that maybe we ask a few too many questions, and you kind of get frustrated and you're like, why are you asking me so many questions? The reason for that is it really helps us determine what's going to be best, and there might be that little bit of information or maybe that one little note of maybe something you need, a compliance you need, or an aesthetic thing that you might need that really might completely change the route that we were going in from a material selection standpoint. So that's why we ask all these questions, and we try to be upfront with information and maybe the reason why we go down that path. But just keep in mind There's a reason we ask so many questions. We want to get you the best material for that particular application. And then you'll notice here there is a link here to our product line card. If you guys haven't seen it, gives just an idea of some of the materials that we represent. So getting into the polymer chemistry of it a little bit, thermoplastics, which is what we deal with, they fall into two categories. You're either semi-crystalline grades or amorphous grades. So what does that mean if you've not heard those terms? Semi-crystalline means the materials have dense, tightly packed regions known as crystals. So they have little, very formed structures that give it some of their properties, and we'll get into that a little bit. And then amorphous, if you take the literal definition of it, is without, and morphous meaning having shape or form. So without shape or form, without structure. There is no structure to your amorphous materials. So what does that mean? That's all fine and good that you explain that to me, but what does that mean as far as performance when I go to pick a material? Amorphous materials, they're going to have random structure. They're typically going to be transparent. There are a few exceptions to that. They're going to have a gradual softening point upon heating. So as I'm heating it up in the barrel to run it, it's going to gradually soften. They tend to shrink a lot less because they have to expand less when we're running them. And they also have better dimensional stability and resistance to warp because they shrink less. So they're able to hold tighter tolerances than a semi-crystalline material. Semi-crystalline materials, they have highly ordered structure. They have those crystals we just talked about. They are typically opaque. Again, you can find some exceptions to that. They have a sharp melting point upon heating, which is going to be your TM. We'll talk about it a little bit more. They tend to shrink more because they expand more when we're running them. But they also have, because of the crystal regions, better chemical resistance, typically. We'll get into it a little bit more as well. Better wear performance and better fatigue properties than amorphous materials do. So again, we explained kind of what they are. Here's some of the different materials that you may or may not be working with already, so you can understand what category they fall into. So your acrylics, your styrenics, your PCs, your PEIs, the Ultems of the world, they fall under the amorphous category. And then your polypropylenes, your different polyamides, nylons, your polyesters, they are semi-crystalline materials. So you'll see over on the right-hand side, a nice typical pyramid, material pyramid. You can't talk about the materials without a material pyramid. On the right-hand side, you'll see the semi-crystalline grades. On the left-hand side, you'll see the amorphous materials. And it goes from commodity at the bottom down here, engineering, specialty, as I'm sure a lot of you guys have seen this pyramid before. So the process of material selection. So now we start getting into it. We kind of already talked about why. We talked about chemical structure a little bit. Now we're going to talk about the selection process. And it's good to understand that successful material selection is going to depend on early and accurate understanding of application requirements. And the reason we say early is because we don't want to get into something where maybe we've selected material, we're moving forward, we're cutting a tool, and then we find out, oh shoot, we need this special type of chemical resistance, but we've already cut a tool to an amorphous material. And knowing that semi-crystalline shrink more, but because of the crystals have better chemical resistance, well, now we've kind of shot ourselves in the foot a little bit because we are going to have to figure out what we can do to maybe meet that shrink, but still also give us the chemical resistance that we want. So if we're able to do it ahead of time, perfect, because then it makes it easier and we're more likely to be successful at what we're doing. So the 5 steps, you don't necessarily need to do them in this order, but if we can have all of them kind of met in the beginning of this project, great. So what we're going to do first is we want to define the requirements of the application. So that's almost like an overhead across the other steps. We need to know what is required for this part. What's going to be required when this part is in application? So part of that is going to include weighing the requirements. So you might find that you're going to have some must-haves, and then you're going to have some wants for these different materials. And that will come down to, again, what's important for the application. Then we want to understand or define the environment that the application is going to be in. The last thing we want to do is to take all this time, find the perfect material, and then find that maybe we put it in an elevated temperature situation that it's not going to withstand those temperatures. So that's the last thing we want to do. So we want to understand ahead of time, hey, in application, what is this going to be exposed to? Then we're going to talk about the key material properties and approvals. So does my material need to have a particular physical property, a certain strength, a certain stiffness? Am I going to need certain approvals? Do I need an FDA approval or compliance, excuse me? Do I need a medical approval? Do I need NSF? So we'll talk about that a little bit because we might, again, find you the perfect material, find out that you need to meet NSF 51 for food contact, and now we're in trouble because the material we selected doesn't, and we have to go back to the drawing board. And then lastly, we want to understand the part design and ease of manufacturing, because maybe you have a part that you want to design or you've already designed, and we're trying to get it into a particular material, but then we find out, well, based on how thin it is, this material really doesn't like to flow in those really thin sections, so we're going to have a trouble trying to position that material for that particular part. So just some things that we'll go over each one, but these are the 5 steps that we like to consider a nice overall understanding when we go to select a material. So we're going to start with defining the requirements of the application. So what you'll notice is these pages are set up. There's going to be a lot of questions. It's just stuff to kind of get you thinking. If you've never really asked this question or been asked this question before, it's something to consider because it could start to, again, lead us in a different direction for how we're going to select a material. So some people might have heard the term CTQs. It stands for critical to quality. And so it's what is going to be critical for this part to work in the application it's supposed to. So some of those questions you might ask from a nice overview would be, is this a new or existing tool? If it's new, then we can pick the perfect material. We can have it cut to the right shrinkage, all as well. If it's an existing tool, now we have to try to fit into the shrinkage that already exists, or maybe potentially slight modifications if you're able to. But we have a little bit of criteria already set up as far as processing is concerned for that material selection. The other thing would be, where and how is the part being manufactured? Am I making this here? Am I making this in Florida where it's maybe a little more moist and so you have more moisture in the air? Maybe the nylons are a little bit harder to run, or you just need to make sure you're doing really good at drying. So just another thing to think about. The other one, where's the part being sold? If I'm selling it to California, am I going to need California Prop 65? Something again to think of. Am I selling it to Europe? Is it going to need EU food contact? Just things to be thinking about. We want to make sure we know these ahead of time so we're getting materials that are meeting what you need. Aesthetics, how's the part need to look? Regulatory approvals, talked about that a little bit. What environment it's going to be in? Is it going to see chemicals? Is it going to see heat? And then what type of load, wear, or impact is the part going to see? When I use this part in application, is something going to be hitting it? And am I going to be throwing it up in the air and letting it hit the ground? We just want to know these things so we can really make the best decision for the material that we need. So now we're talking about weighing the requirements. So sometimes you'll come and your molder, or you as the molder, might come and say, hey, I've got all these requirements for it, but now we need to start to figure out if there's a lot of really distinct requirements. There might not be a material that matches every single one of what you've picked out. So maybe we start figuring out what's the absolute most important, and then what are going to be considered some wants, but not going to be needs as far as if the application will work if we don't have it. So what does that look like? Just a quick little example for you guys. So let's say you come to me and you say, here's my requirements. I need a soft material, TPE like type material. It needs to be in the 60 short A range. I'm going to need it to chemically bond to polyamide nylon. It's going to be an overmold grip. It absolutely has to bond to it. It's going to need to be colorable. I want to make it in pink, green, blue, maybe other colors. It needs to be available in bags because it's easier for me to load my machines that way. It needs to be FDA compliant. I do not want it to need to be dried. So now I take these requirements and I can look at them in a different setting. What are my must-haves? I absolutely have to have FDA because it's going to come in contact with food. It absolutely needs to bond onto the nylon because the main part, hard substrate, is a nylon material. So I'm going to need to bond to it. It needs to be a soft material in the 60 short A range. Maybe plus or minus a little give, but it really needs to be in that range. But I also definitely need it to be colorable, pinks, greens, blues. This is how I start to differentiate my products by the different colors. And then what are some wants? Available in bags. It's not going to be imperative that it comes in bags necessarily for me to be able to run it and make a part, but it's something I'd like to have if it is available. And if it doesn't need to be dried. I pretend I'm a molder, I do have a dryer on the floor, so I can dry it if I had to, but I'd prefer not to, so that becomes a want. Some other different scenarios of this, maybe this isn't imperative that it's colorable. Maybe if we could just do a natural and a black would be fine, but it all comes down to figuring out for your particular application, what are must-haves and what are want to have. And you'll notice on a lot of these slides, I don't bring up cost because I think everyone ideally would like to have a low cost. And in some cases, it very much is a must-have that it must be under a certain price, but I don't bring that up in here. So just as an FYI, it is not in these slides. we'll go through another one. Let's say I need a clear V0 at 3mm rated, flame rated material. Needs to be high flow. I'd like a service temperature of above 100 C. I'd like it made domestically, and I need to have an ISOT of greater than 2 foot-pounds per inch. So now I take that and I figure out, okay, what are my must-haves? What are my wants? My must-haves are, I absolutely have to have the flame rating. It's kind of important. It also is going to see 100 C plus service temp, so I absolutely need something that can withstand that. And it's going to be in an impact test. So I know that I need to be above the 2 foot-pounds per inch. I've already figured that out during my processing and all that this is what's going to be required. So now my wants, in this case, having it be clear is a want. It doesn't necessarily need to be clear for this application. It's not going to be, it's not going to be detrimental if it's not clear, but I'd like it to be clear. And high flow, maybe in this particular case, the nominal thickness is around the 3mm, and I'm okay if I don't have a high flow. I'd like to, but I don't need it. And then same with being made domestically. I don't absolutely have to have it made here, but maybe if I just have it readily available, maybe it's something you stock or we stock as Chase, it's in stock, I can get it quickly, but doesn't necessarily need to be made here. And then there's other cases where maybe it's some type of, maybe it's a military application and it does need to be made domestically. Again, it's for you guys to decide when you're looking at your requirements that you determine what is a must-have and what's a want. And if we can differentiate that and start to figure out that, it makes it easier for us to get you exactly what you need, and preferably what you're wanting to get as well. So now we're talking about the environment a little bit and how those will affect your application as far as maybe properties or performance, because it's really good to understand where is my part going to be or your part going to be when you mold it, what is it going to be seeing. So what does that look like? So what is the environment the part's be exposed to? What are the temperatures it's going to see? What is the chemicals that are going to come in contact with it, be it accidental or submersion type exposure? What is it going to see for UV? Is it outside? Is it going to be outside for a long time? What are the stresses? And what are the wear and friction type applications? Am I making a gear? Am I going to need to have something that's going to be good for wear and friction in a gear application? Am I not? So just some of those things, again, keep thinking about this stuff as you're going through your application and you're starting to select materials for these applications. So some questions that you might see come up when you're talking about certain temperatures and exposure temperatures. So the first one would be, is there going to be a temperature that's going to be exposed to an elevated, or maybe it's a cold temperature, maybe it's outside and it's, it needs to see -40 C. How long are you going to be exposed to that temperature? So it's one thing to say that I need a material that resists this temperature. Okay, is it seeing it for 10 minutes? So it's more of just a peak where it might see that for a little bit. Or am I going to see that temperature for 5,000 hours? And I need it to be more of a continuous use type temperature for 5,000 hours. And then the next thing would be, what is the expected performance at that temperature? If I'm at that elevated temperature and I lose, let's say 50% of my initial performance, is that going to be a problem or is that going to be okay? So it's things that we need to understand when we're making these selections, because the higher temperature materials you get, generally, the more expensive they are. So if we can find you a nice medium that gets you exactly what you need from a temperature performance without being overkill, that's what we're going to try to do and be that consultant and get you that grade that's going to work without it being too much. So we need to understand then what is the requirement for that. So you'll see here, there's a little graph. It shows you the performance of nylon. And so the elastic modulus would be its stiffness. And so what does that look like across the varying temperatures? So you might find that depending on what you're able to use as a performance indicator, maybe you're looking at 100 degrees C. Well, depending on what your requirement is for modulus, the polycarbonate is way outperforming your PA6. Maybe you can use a huge loss in properties, but it still needs to hold something at that 200 range. Well, you can see that your nylon 6 now is starting to outperform the polycarbonate. So again, it's just one of those things where you have to understand what you're looking for specifically and what type of performance is required at that temperature. Another couple really cool graphs here. You'll see this one over here on the left-hand side is nylon with different glass loadings. So you see the unfilled performance as far as the stiffness is concerned, and then the 40 glass. But you'll notice there's still a temperature at which you're not going to get the performance anymore. So understanding that and knowing what temperature your part's going to see might say, well, Nylon 6 is out because I need performance at 250C, or whatever it may be. So we need to understand that thing. The other thing too would be if you're going to be in a heat aging type test. That's what this one over here on the right hand side is. The different temperatures you'll see over here, you still maintain decent performance across a whole bunch of hours testing it at 270F. But if you're testing it at 300F or 380F, excuse me, you drop very quickly in performance. So if it's going to be in an area where it's going to see some type of heat aging, we need to know what type of requirement is expected after the heat aging so we can get something that's going to work for you specifically. Another couple key pieces of, I guess you could call it advice. If the temperature of the environment is going to be higher than the glass transition temperature of an amorphous resin, just note that that resin is no longer going to retain any of its mechanical properties or performance. Once I get that hot, it's no longer maintaining any type of performance. It's going to drop right off. If the temperature the part will be exposed to is higher than glass transition of a semi-crystalline, it is going to exhibit some retention of mechanical properties. It's not going to be great. It's not going to be, the same as before the TG, but it will maintain some of it because semi-crystalline resins have the crystal regions that will maintain their structure until the melting temperature. So there will be two dips on a curve when you're looking at the stiffness versus temperature for a semi-crystalline, whereas your amorphous will have one dip right at TG. It's going to lose all of its performance. And so what does that look like? So if you're looking over here on the left-hand side, you can see we take our first dip here. This is going to be the TG. This is a PBT grade. You're going to lose your first little bit there, and then the last bit over here near the TM. So the crystals have no longer kept their structure. It's above that temperature. It's losing its performance. And then you'll see here, this is a PEI material. You've got one dip, amorphous, right after the TG, no longer useful. You're not going to maintain any type of properties or tolerances past that temperature. So again, just one of those things we really need to know what it's going to see. So next we have chemical resistance. We want to know what chemicals the part is going to be exposed to. We sometimes get the answer of, well, it'll see a few chemicals, so we just need good chemical resistance. Well, we can try to do that, and we know that typically our semi-crystallines, because of the crystal regions, will perform better with chemical resistance generally overall, but that doesn't necessarily mean that whatever accidental chemical that might come in contact with your application isn't going to be detrimental to the material that we select. So if we have an idea of the exact chemicals it's going to see, we have a much better shot of getting you something that's going to perform adequately as it should in that environment. We also want to know how long the part is going to be exposed to that chemical. Is it something where it might sit in that chemical for a while, or is it something that it might get splashed on and then we wipe it right off? So that will have a different effect depending on how it's being exposed. And then the other thing is, what's the temperature that part's going to be seeing while it's being exposed to that chemical? So the temperature is going to accelerate the way that the chemical attacks the material. So if it's seeing it at room temperature versus an elevated temperature, the performance is going to be different. So we kind of want to know that ahead of time if we can. The one thing that I did mention, chemical resistance is going to be very dependent on the base resin itself. And so there's not really an additive that you can add to it that's going to all of a sudden give it great resistance to a chemical that would otherwise be detrimental to it. So, and they're also going to vary greatly resin to resin. So like I mentioned, if we know the specific chemicals, we know that we can then find a material that's going to resist them. Because you might find a semi-crystalline that's good with all of these different chemicals, and then the one that you didn't know or wasn't mentioned might attack that nylon now, and now we have a failure because it's attacking it. It's either cracking it or dissolving it, or something could be happening. It's no longer going to perform the way it should. And so also on this, you'll see the little snippet from a guide that I provided. You have it 20 degrees C and 50 degrees C. So you'll notice that some of them perform excellent at both temperatures, elevated and room, but then once you get into an elevated temperature, some of them start perform not as well. So E being excellent, F being fair, G good, and N not recommended at all. And so you'll see on average the polycarbonate, there's a bunch that attack it. It is an amorphous material. It's not as chemically resistant compared to like your polyethylenes and polypropylenes that are your semi-crystalline materials. But again, very dependent on the base resin and the chemical being exposed to. And then the other thing that I'd like to point out as well is when you're looking at different chemical resistance, if we're using a guide, we'd really like to know that the information for, if we're comparing two different materials, maybe we're comparing a nylon and we're comparing it to a PBT. Ideally, if we could, we'd like it from the same guide, or at least know that the conditions are exactly the same. Because in two different studies, it might have been maybe an accidental exposure versus submersion. It might have been at a different temperature. They might have exposed it to a different amount. So if we can get it from the same guide, we're gonna have a better understanding of how the two perform in really good comparison, apples to apples, versus if we get it from two separate guides if we don't know the conditions for the two guides. So just kind of keep that in mind when you guys are looking up different chemical resistance of different materials. Ideally, if we can get it from the same guide, much better. We mentioned this before, amorphous materials, they're less chemically resistant and they're more prone to stress cracking. So that's what the picture you can see on the right, where you start to get the cracks in there because of the chemical exposure. That's what that looks like. And then, as I'm sure everyone's aware, the best way to do the testing is if you can test it in your application. It's the absolute best way to tell if it's going to work or not. In cases that you can't, we do refer to guides if we have them available to show the performance or the expected performance of that material in that chemical. UV exposure. So is this part going to be exposed to UV? Is it going to be outside at any given time? Is it accidental UV? So is it like, you know, you have your toothbrush and you accidentally take it outside and leave it? That's not the expected environment of that material. So you wouldn't necessarily plan on having that for that type of product. But ones that we do know are going to be outside, we want to know how long is it going to be outside? Is it just the occasional comes through a window type thing? Is it a car component that's going to be outside the entire time? And how often is it going to be seeing that UV? So is it, you know, a deck chair that sits out for half the day and then the other half maybe get some shade? It's just good to understand how long the exposure will be for UV, because it's very, if the material is not UV stabilized or a material that's good against UV rays in general, it is going to attack it. You can actually see in the picture below, it starts to discolor it. And in some cases, depending on the material, it will actually start to lose some of its properties as well. So then the question becomes, if we know it's going to go outside, we know how long it will be, the next question becomes, what type of property retention or color shift is going to be acceptable after exposure? So if I leave it outside for 10 years, is the expectation that it's never going to discolor or shift? Or am I going to leave it out for 1 year and a slight shift is going to be okay? One of those things where we want to start understanding, what do you consider acceptable when we start looking at these types of products? So why do we look at UV? UV rays they come through the ozone layer and they attack anything that's outside. So there's three different types. You have your UVAs, which are gonna be your long rays. They are not absorbed by the ozone at all. So they're coming down, they're hitting the plastic parts, and if they're parts that are not UV stabilized or certain materials that are attacked by it pretty readily, they're gonna get attacked by this UVA ray. It's gonna start to discolor it or ruin some of its properties. UVB, they're going to be medium-sized rays. In parentheses, you'll see the wavelength in nanometers. They are mostly absorbed by the ozone, but some still get through, so they can still be detrimental to the plastic parts. And then UVC are short wavelengths that are completely absorbed. So if you look over in the table, if the activation energy is around that range for UVC, it doesn't occur naturally outside. So it'd have to be either they're using it on purpose, as sometimes they'll use it as a germicidal type application, they'll hit the part with it. So we gotta be able to resist that. But if we're just setting it outside, it's not gonna see UVC. So you'll see in the activation wavelength, materials like your ABS, absolute horrendous UV resistance. You'll see that the wavelength exposure and the activation wavelength is kind of right in that UVA range where all of them are getting through the ozone and just attacking it. So stuff like that and ABS, we will absolutely never recommend if it's going to be outside, because it will start to discolor. And so just knowing that in application it's going to be outside, we start to make different decisions for our materials. Then a nice little table for you guys. They kind of go across which ones have really good UV stability, which would be, they could be formulated with little or no UV stabilizer. So it's going to be your fluoropolymers, your acrylic materials, and then it goes all the way down to ones that we just don't really recommend at all if you can help it. So that'd be your aromatic TPUs, your ABSs, HIPs, And then the ones kind of in the middle are if we just make sure that we properly formulate it with a good UV stabilizer, it could be used outside readily. So your stuff like your nylons are used outside a lot, ASAs, TPOs for maybe bumpers on cars, stuff like that, easily used outside with no problem, as long as it's got a good stabilizer in it. So the next thing we want to talk about is we want to determine the material specific properties and or approvals that this will need for your application. So do I need, FDA? Do I need, a certain impact level? So we want to start to really drill down into those specifics, because we know maybe you have an existing application that's similar and you know that you need a particular flexural modulus to meet the stiffness requirement you have, or maybe it's going to see impact and we know that if it's under a certain impact level that we can correlate back to a data sheet, we know that it's not going to perform well. So this is where we start diving deep into, now we've kind of got a family idea of what material we want to be in. Now we got to start looking at grades and how they're going to perform that way. So some material properties, some questions we might ask about the physical, mechanical properties of the material. What is the stiffness requirement? So the modulus or flex mod of that particular material, what's going to be required? What is the impact requirement? Again, one of those things, maybe I throw it up and it needs to withstand it. Maybe it's my phone case and I need to have really good impact because I'm probably going to drop it in my driveway and hope that I don't shatter the screen. What is it going to be expected to withstand? Is there going to be a load on it? Is there going to be stress? What is it going to see as a part that I'm going to make sure that I design to have it withstand that? Is the part going to be flexed, bent, assembled, or am I going to do it repeatedly? Is it a phone case that I'm going to put on, take off, and keep doing it a bunch? Is it a DVD case that I'm going to open and close a whole bunch of times, so the living hinge on it needs to be good and needs to be allowed to open and close hundreds of times? So it's just, again, understanding those things puts us on the right path to getting you the right material. Some questions ask about the aesthetics. What color are these parts going to be? Do I have an idea that maybe I want it to be glow in the dark? Does it need to be a bright fuchsia pink? So these questions need to be asked because there are particular ones that are difficult to color. Is there going to be a texture on it, a certain feel? Do I need it to have a certain polish? Some materials are more aptly able to do that kind of stuff and some are not. So we need to know what the expectation will be for that. So in line with the aesthetics and the color, some materials, because of their base appearance, be it base appearance, reinforcements, fillers, sometimes additives, they are difficult to color and to meet certain colors. So what does that look like? If you have a material, commonly nylons, if they have moly lubricant, this is actually the natural appearance of something with moly in it. It has a gray color. So I'm obviously not going to turn around and have a bright pink color if it already comes in gray. It'd be very difficult to do that. PPS, your Rhyton type materials, they come with a dark tan color. Some of the newer generations are a little bit lighter, so they're a little bit lighter brown, but you're still combating a brown color to start with to try to get to it. So as you can see, the ones over next to it have been colored green and blue and pink, but that's about as vibrant as you're going to be able to get because of the base color you're trying to fight in the beginning. And then materials like phenolic curled TPVs, so standard TPVs, if you get them in nat, they have little black specks. That's completely common. So you can see kind of right in the middle one, there's a little black speck there. So if that's going to be a huge problem, we're not going to want to use a TPV in that natural, at least not a phenolic cured one. There are other ones that are peroxide cured that will not have that, but just it's one of those things that if we know that ahead of time, we can make sure we get you the right material for it. And then another note that I do want to make is that if there's particular regulatory approvals, maybe it's a UL approval, a medical approval, you might not be able to color at the press without losing the approval. So if you're taking a particular color that's not approved to be used in that resin for a flame retardant grade and you're mixing it in, you're likely to lose your UL yellow card rating for it. So just another thing to keep in mind, we're talking color and we're talking about what's available. In those cases, if we can, we'd want to get you something pre-colored so it maintains its listing. So just more things to think about when we're trying to select materials. So now we'll get into the regulatory approval portion of it. Does it need any approvals at all? Do we need a UL flame rating? So it has to come with a yellow card. Does it need to be NSF approved? Are we looking for something that's going to be NSF 14, NSF 51 for food? what have you. We'll need to know that ahead of time. And then are there any other industry standards the part might need to meet? Do you have an ASTM call out? Do you have maybe a military call out? Do you have maybe one of the tiers in the automotive industry and they have their own particular standards that we have to meet? If you know that we need to meet it, if you can communicate that with us, it makes it easier for us to review what's required of the material and make a selection for that particular material. Some other things that you might see or have heard of before, been asked for regulatory approvals. There are ones that are actual approvals where we'll have either a letter on file or a certification for that particular grade of material that would be selected. That would be your USP Class 6, which is the most common one asked for. That's the biocompatibility medical approval. So our materials will come with certifications for that. The Underwriter Lab, that would be your flame ratings, your UL 94 flame ratings. There will be what they call yellow cards available for it for that particular material grade, so you'd be able to get that. And then NSF on their website for NSF 14 for piping, 51 for food, and 61 for potable water. There are approvals, they approve it. You can pull the cert from their website. And then there's other ones that are going to be considered compliances, your REACH, RoHS, Prop 65. This is saying, you know, either we do or don't have any of the restricted substances in this material, and they let you know that ahead of time. It's not a pass-fail type compliance, if you will. It's yes, it has something in it, or no, it doesn't, and you have to mark it as such. And then you have FDA for material specifically. FDA doesn't approve materials, so we'd have a letter saying it's compliant. It doesn't have anything it's not supposed to in it, so it would be good to use in food contact. ISO 10993, if you guys have seen that, it's for medical. It's technically, as well as the FMVSS 302, they're part approvals. So it's technically supposed to be done on a part that's being produced, but some suppliers will have data or have tested it on a particular size product to say, yes, we are compliant. If you were to do your own testing, yes, we would be compliant. You would pass because we've done it on a sample part or a sample plaque that shows that we passed that. So just some ones you might have seen out there, but these are going to be important. We need to know these things. If you say that we just need something, and then at the tail end of selecting material, you're like, oh, by the way, we need a medical grade. Absolutely, we'll probably turn around and have to get you something totally different because that's probably not the route we were going in to begin with. So if you know these things up front and you're able to let us know, perfect, because then we make sure we go down that path in the beginning. And then finally, we want to understand the part design and ease of manufacturing. So part design, what's the nominal thickness of this part? If it's a really thin part, there's certain materials that just do not flow well that we're going to have a hard time utilizing in that part if it's a really thin part that's being designed. What's the expected flow length? Am I only going to gate it once and it has to flow the full 5-6 inches, or am I going to have 3 gates and then I have a much smaller flow length because of the 3 gates? And so that kind of leads into the how and where is this part going to be gated, because then there's questions of how am I going to gate it, stuff like that when you go to process it, so things to be aware of. And then the pictures that you can see underneath, this kind of goes back to the thickness and how well it's going to flow. You can see at the varying material thickness, so the thickness of the part, how well it flows. So you can see that if we get to about 2.5 millimeters, I can get the full 600 millimeter flow out of a nylon 6 material, but I have to go all the way to a 5 millimeter to even think about getting that type of flow length out of a polycarbonate because it pushes so much harder. So the thinner the part, the less likely I am to recommend something like a polycarbonate that's going to flow a little bit thicker. Or in the case of potentially I move to a high flow polycarb. So again, something if we know, we can start making the right suggestions based on that. And then ease of manufacturing. So this comes into whether it's your shop floor and you're the molder and you're making these decisions, or you're an end user and you're going to have a molder mold these for you. We need to understand what are their capabilities. So what type of conversion process first is going to be used to manufacture this part? Am I extruding? Am I injection molding? Maybe I'm thermoforming. We need to know these things because certain grades are going to lend themselves to certain processes that others are not. The other thing would be what type of processing temperatures are going to be needed. So maybe we have some high temperature nylons and you're going to need something like oil to cool your mold, if you want to call it cooling the mold. whereas you can't get away with using water. But if that's not something that's available to that molder, well, now we're going to have a hard time recommending a material that was going to require that. What does the material need to be dried? Do we have the appropriate desiccant dryers if we're going to use a material like maybe a polyester that really needs to be dry well for it to run well? If you don't have the desiccant dryers to do it, it's going to be a hard time trying to run those materials. And then the question we kind of brought up a little bit, how difficult it's going to be to degate it or demold the resin itself. Is it going to want to stick? Is it going to have a problem coming out and getting the gate off it? The other question would be, is cost going to be a thing? Are we going to have to make sure we're at a really low cost? But then you start getting into what you have to give up to get to a certain cost point. So there's trade-offs between it. And then finally, are we trying to match shrinkage for an existing tool? We talked about this a little bit, but if we know that there's a tool that already exists, we know that there's a particular shrinkage that it was made to. So we want to try to match that as best we can to try to keep the part in tolerance. So that's something we need to know ahead of time as well. So now we'll kind of get into some quick examples. These are just some quick ones I threw together to try to go over the different parts. So for this particular example, we're going to make a toothbrush. So our requirements in this case would be, I'm going to need it to be FDA because it's going to go in someone's mouth to brush their teeth. I want to make the entire toothbrush, so I need to be able to do both the hard substrate and the overmold for a nice soft grip on the toothbrush. It needs to come pre-colored. I want to have it, in this fun white or green color for the two different hard substrate soft plastic. I need to be able to injection mold it because that's how we're going to make the part. I want low cost, I want it available in boxes, and for the soft touch material, I want it in the 80 Shore A range. So now I've kind of defined overall what I'd like it to look like. So now what we do next is we're going to start to weigh the requirements. What is my must-haves for this application? What are wants? My must-haves is I absolutely need it to be FDA. It's going to be in someone's mouth. It absolutely needs that. I need the hard substrate and the soft touch plastic to overmold. I need a chemical bond because there's no way to do an interlock on that on my particular design that I'm doing. So I absolutely need a chemical bond between the two. So when we make the two material selections, we need to make sure that they bond. They absolutely need to be injection moldable. I'm not trying to run any other conversion process, so they absolutely need to be able to be injection molded. In this case, it absolutely needs to be a low cost. I didn't put a specific value on it, but there's a value there that if I go above it, I'm no longer going to make any money trying to make these toothbrushes. So it's absolutely, in this case, a must-have. And then I absolutely need it to be an 80 Shore A. I don't want it to be too soft. I don't want it to be too hard. I want it at an 80 Shore A. And so then my wants become available in boxes. I could get away with bags if I had to. I don't really want to, but it could. And then I don't absolutely need it to be pre-colored. However, though, I still need to get those colors. So I am going to, if I have to use a colorant, I do need to make sure that I have an FDA colorant to be used as well. But these are how I've started to mold my application into what I absolutely need versus what I'd like to have. So next would be, now we understand the environment of it. I kind of know what I need it to do, what I want. I know that there's gonna be no elevated temperatures. And if there were, then there's a problem because this is not gonna see elevated temperatures. There's really gonna be no UV exposure. There might be accidental exposure, but I'm not gonna design to that or get a material for that because it's not meant for that type of application. And then chemical resist, it needs to not be, we can't have toothpaste attack it. We'd have a problem with that. Then we talk about the properties themselves. So we've already mentioned we need the FDA compliancy because we need it for both the hard and soft substrate. The whole thing needs to be FDA. I need the chemical bond between the two. I need them colorable. If they're not already coming pre-colored to me, I need the 80 Shore A. And then I also have a requirement for flex mod. I know in this particular case, for this one I'm designing, it needs to be over 250 KSI, so it'll be 250,000 PSI flex mod to keep the overall stiffness for the toothbrush. I don't want it to be too flimsy if I'm trying to brush. I don't want it to be kind of flimsy all over the place. And then also I need it to be Reach, Rojas, and California Prop 65, because if I want to turn around and sell these on Amazon, if someone goes to buy it in California, I don't want to have a big old label that says, it contains such and such, because if it's getting sold to California and it does contain something it shouldn't, it would have to be labeled as such. So I want to make sure that I get materials that I don't have to label like that. I can sell it in California without an issue. So that's another requirement and approval that I need for this particular product. So now the part design and ease of manufacturing. I'm going to use a two-shot process. I happen to, in this scenario, have a mold that I can use two-shot, so I want to be able to do that. It's a new tool. I haven't made these before yet. I've made something similar, but it's a new one, so I don't have to match any shrinkage. So that's good. We kind of have free reign to pick the best material for this application without having to match anything. And then my molder does have dryers if they absolutely have to. Again, I had a want of not having to do it, but if they have to, I do have dryers. And then they do have feed throat blenders to color at the press as needed. So in this particular case, if I was to look at this overall, what would probably be recommended at this point to meet my requirements is I'd likely look at something like a propylene, maybe a homopolymer, get a little bit stiffer than the copolymers. I would meet my flex mod that I needed. Probably a 20 mil. That way, if I put one gate at the end, I can shoot it all the way through. No problem with it being a little bit thinner. Not an issue. I wanted an FDA. And typically with your commodities, they come in natural. They're produced in natural in rail car loads, just huge quantities. And so I'll take it in natural and then I'll color it if I wanted to have that really nice white color. And then for the overmold, I'd probably go something like a styrenic based TPE because I know that it will overmold and chemically bond to the polypropylene. So I get my 80 Shore A, I get a polypropylene overmolding one, and I get an FDA one because again, huge requirement, FDA. So we have one more quick example of something like this to kind of walk through it again. So this time I'm going to make a flagpole bracket. I'm going to have it so I can put it on the column at my house, put a flag in it. My requirements, although the picture is white, I want it to be black. I want it to be a black bracket. Of course, I need UV stability. It is going to be outside. I'm going to injection mold it, so I know I'm going to have to use that. I want availability in bags, and I do know that I need the stiffness and strength to hold the flag. I can't have something that's flimsy. I go to put the heavy flag in it, and it just bends it. It's not going to work for me. I need to make sure that it's got the stiffness and strength needed to hold it. So now I take my requirements and I start to weigh them. Absolutely need the stiffness and strength. A must have. Again, can't have something flimsy. Absolutely need the UV stability. It's going to be outside. It's going to need to resist it. I can't have a huge color shift and I can't have it lose properties because if the properties that it lost were stiffness, well, now it might not hold my flag anymore. And I need it to be injection moldable because that's the process I'm going to use to make it. My wants are availability in bags. Again, maybe in my shop, my floor, it's easier to load them up, so I want them in bags, and availability in black, because if it's not available in black, it's only available in natural, I could add black colorant if I had to, but I would prefer to have it in black if I could. So now the environment. So we know that it's gonna be outside, so you're gonna have your outdoor temperatures, so you start to come up with the range that you think it will use. So we have outdoor temperatures ranging from -40 to 110, so that would be just a range that you estimate will be what will be seen outside. So I want to make sure it's going to resist that. I'm going to have constant UV exposure with the exception of, the few houses that maybe the shade gets it on a certain time of the day. But for the most part, it's going to probably see consistent UV. And then I don't really expect any chemical exposure. If something happens and you're getting chemicals on it, it's not meant to. It's not in an area that you would expect that. So you're really not going to design for that or pick a material for that. Then you have, so now I want to talk about the properties itself and approvals for the material. UV stable, so it needs to be UV stabilized grade. Colorable if it's not already black. So if it's a material that would be difficult to make black, which I don't know if really any that are necessarily, but I do need to be able to make it black. And I know for my flex mods, my stiffness, I needed over 300 KSI or 300,000 PSI. That's what I've determined based on maybe prior knowledge or what have you. That's the requirement that I have. And then the last one would be, I do need California Prop 65. I want to be able to sell it in California without having to put a label that it contains something that would be a problem. So I want to be able to make sure that that material has that particular compliance. So now I want to know when I go to mold it. So in this case, I'm going to injection mold it. We already mentioned that. But in this case, it's different. We already have a tool because I've made something similar to this in the past, and I already have a tool that I'd like to continue to use. Or maybe a tool comes from another molder, but a tool already exists for this particular part. So now I know when I'm going to select a material for this, I have shrinkage to match. So in this case, the shrinkage that our imaginary tool is made for is 15 thou inch per inch. So I know that I need to match that or be very close to that when I pick a material specific for this program. And then also, the molder or myself in this scenario, we have dryers if we need to dry the material, if we pick a material that needs to be dried, and feed throat blenders if we have to color at the press if needed. So if we don't get, you know, it already pre-colored black, I can then color it as needed. So in this case, we went with a UV black polyamide 6.6. Because there's no real temperature requirement, you could also do a 6. There's, you know, the ones there. But I know that in this particular case for this grade that was being looked at that we have in mind, there's a black one. It's already UV, does come in bags, which is what I wanted. It's got 450,000 PSI flex mod. And then the shrink range for that PA66 is 14 to 16 thou. So that 15 thou kind of goes right in the middle there. So I should be able to match that shrinkage and really not have a problem. So now it's something where I can get me a bag and try it, and I can start looking to use that material for this particular application. So with that, that is all I had for you guys. I had the couple examples and went through that, and I'll hand it over to Jason. He wanted to go through these last couple slides for you. And then if you have questions, feel free to put them in the chat box. We're going to address those as we move forward.
Wonderful. Thank you so much, Andrea. Fantastic presentation. For everyone still on the line, we are open to questions if you're so inclined, either via the chat box or by raising your hand through the control panel for the webinar. So if you have any, feel free to type them in. And if there are any questions, I'll address them as they come in. In the meantime, I just wanted to reiterate, as I mentioned at the beginning, we do have another webinar coming up in February focused on the types of PPE materials that exist and what their advantages are. That will be Wednesday, February 10th from 2 to 3 p.m. Eastern. And we'll go over a few things, the type of PPEs that are out there in the market, what the differences there are, specifically looking at standard TPEs, TPVs, TPU, and copolyester elastomers. We'll go over a few of the limitations of some of them, as well as common application and market uses, and Q&A as we're about to do here. I do have, looks like at least one question. Oh, it just went away. If you could raise your hand one more time, that would be fantastic. Hold on 1 second, I'll get you unmuted and you're welcome to ask a question. All right, Tom, you can go ahead and ask your question.
Hi, Andrea. This is Tom White from Grand Traverse Plastics. Can you hear me?
Yes, we can.
Oh, okay, great. First off, that was a great presentation. Thank you very much. Secondly, I'm going to propose a question, and I want to hear how you would answer it. In our world of molding lots of nylon, we commonly hear from our customers, which would be the big auto guys, they want a nylon 6 for a nylon 6.6 for every application because it has higher heat resistance. And yet, every intake manifold that I've ever seen on the globe is made with nylon 6. And so our response is always, if the part's not structural, in other words, it's not a bracket under the hood holding something out in space, it just has to be dimensionally stable and it's bolted down in lots of places, like say an engine cover. We prefer nylon 6. It looks better. It holds its dimension through heat cycling better, it seems to, at least from what we see. And yet, maybe it's accurate, but it doesn't seem to be accurate to me, the belief that nylon 6.6 is better when it comes to heat resistance. How would you answer that?
Sure, I will actually let Jason answer this one for you. He's our auto guy, so he's gonna have the absolute best response for you on that one, I'm sure.
No problem. You're right in a sense, Tom, that depending what the actual performance needs of the part are going to be, and I'm talking about loads and durability specifically, can sometimes get around the need for nylon 6.6. There are also at times, it's worth noting that depending on the temperature and exposure lengths, at times nylon 6 can actually have a more stable operating condition over long term. So it might have a lower threshold of properties off the bat compared to nylon 6.6, but when you look at percentage of property retention on a long enough timeline, there are advantages at times, like I said, to using nylon 6. Now, there's nuance to that, right? And being glass loading or mineral loading and the type of heat stabilizer package that's used. But yeah, there are plenty of times where nylon 6 at heat will outperform nylon 6.6. Now, typically there's a temperature threshold, but it's rather high for nylon 6.6 to not withstand it.
When would you say nylon 6.6 is the way to go?
Ooh. We're talking like 3,000 hours plus exposure. I'm assuming, that's kind of the crux of it, and because we've seen a lot of changes in heat stabilizer packages over literally the past 2 years, and the way that they're trying to design nylon chains to maintain a certain level of durability out past 3,000 hours. I'd be hesitant to say exclusively. We try to take them on a case-by-case basis.
Okay, thank you.
No problem.
Jason, it looks like we have a question here from Tony. What are some of the greatest challenges when determining material selection, and how can we get around or ahead of them?
I would say, yeah, so I would say it depends a little bit. I would say overall, the largest problem would be if there's something that already exists or a mold that's already been made for maybe an amorphous versus a semi-crystalline, and then the requirement of the application is more in line with the performance of a semi-crystalline grade or amorphous grade. And so that is what I find is our biggest struggle. And then the other one is we do tend to sometimes get a little pushback when we ask additional questions for more information on the particular application. So a lot of the questions that you saw in the presentation, we tend to ask those questions or, a variance of some of them to really dig deep into what we're looking for. So we sometimes get a little bit of hesitancy to give us all the additional information up front. So that's what I see a lot of times as the biggest struggle, is we might be going down this path and all of the requirements that have been provided to us thus far, we found this, perfect material. This resin's gonna be great. It's the cost where you want it. It's gonna run great. And then we get hit right near the end and they're like, oh, by the way, it needs to do this, that. Now we have to revert back and go all the way back to the beginning and start to narrow down our choices with this new information that's been provided. That's what I've seen has been, I would say on our end from the material supplier and the ones that help with material selection, our biggest problem. So, and we'd like to put it out there that we're here to help you guys. We want to be really good consultants for the different materials that are out there and available. So if we could see a little maybe less hesitancy and maybe a little more information up front when we're here to help you, that would really help.
And Jay, did you get the question from Matt yet? Did you?
Yeah, Andrea, the question is, can you educate briefly on conditioning nylons and the methods for filled versus unfilled?
I'm sorry, you said conditioning nylons filled and unfilled?
Correct.
Yep, so nylon materials are unique in the fact that a lot of our materials do need to be dried, and we want to make sure that we're within a certain threshold before we run them, because you run the risk of going through hydrolysis. So it's going to be the breaking down of the molecules when you're running it. So the exposure to the high temperatures when you process can start to break them down. One kind of caveat to that, if you will, is there's still a threshold for an upper limit on your nylons. You want to make sure that you don't go past that. But there also is a lower limit that we'd like to stay above. So there is kind of a range when you run your nylon materials, that if you can stay within that range, it'll be great. Problem being, the water and moisture does plasticize the nylon a little bit. So if you dry it too much or over dry nylon, it starts to become brittle. And so the issue can become, now you've got a brittle part, whereas in normal cases, it would run fine and be a perfectly good material for that application, or just in general, that part would be a great performing part. But because maybe we've over dried it, now we have a problem. And so one way around that is you can condition them. So you put them in the presence of moisture. A lot of times, maybe depending on the size of the part, you put it in a bag that's got water in it. That's what I've seen of. Maybe Jason, you've got some other methods for that, but then you can start to introduce some of the moisture back in a little bit, so it gives its ductility back instead of being, you know, a really brittle part.
Yeah, I would agree with you. The biggest question is, you know, how dry is the part and how quickly do you need to recondition? So at ambient temperatures in 50 degree or 50%, excuse me, relative humidity, it may take, you know, a couple days or more to condition. To really depends on the level of moisture you'd like it to get to as well. So unfortunately, there's more nuance to the response than I would hope. But, you know, generally, if it's just for parts that are being packaged in that need to have some ductility during assembly or something like that, I think dropping the water droplets in with the packaging is sufficient. With the strong asterisk annotation on this, that nylon, if it absorbs moisture, it will lose it just as quickly if it's placed in a humid setting. So if ductility is needed, if it's somehow going to be exposed to a more arid environment, then we tend to lean more towards impact modification of the polymer rather than relying on moisture content alone. I see that Evan Schneider has his hand up. I'm gonna, if you could unmute yourself on your end, feel free to ask away. Evan, it looks like you're unmuted now, but I'm not hearing you, unfortunately. Okay, perfect. You're going to type it in. Thank you. In the meantime, I see that Doug Thompson has a question as well. What are the considerations and options when using an existing tool?
I would say the first one, obviously, as we mentioned, the existing tool would be somewhat dependent on what type of changes they'd be willing or able to make to the tool. Is it something where, you know, we can adjust maybe the shrinkage it's built to? We can make some tooling changes to adjust that accordingly. If absolutely not, then what we do is we try to find a material that's going to get close. Maybe potentially we use some sort of filler if we can to maybe limit. So let's say we're doing, you know, an amorphous material and we want to use a semi-crystalline. We know the semi-crystalline is going to shrink a lot. Maybe we add some type of reinforcement or filler, which is going to start to decrease the amount that it's going to shrink. So we have, it gets kind of closer maybe to an amorphous type product. So what we can start to do is we just figure out what the requirements are and why we'd be moving to a different material for an existing tool. And then we adjust accordingly. So is it, you know, it's already set for amorphous and we need better chemical resistance. Well, then we try to see what's going to work best for that and then see what type of changes either from the tooling side if we can, or if we have to add some type of filler reinforcement to get it to shrink less, to get it as close to what's going to be considered the tolerances for that part as we can.
Okay, if anybody has any other questions, it looks like Evan was able to type his on here. Jay, if you want to read that one.
Absolutely. And this question is, how does crystallinity vary by processing? I would assume that there many polymers are borderline and can be made more or less crystalline based on cooling rate and processing. Is there a hard line in categorizing plastics, or is it all a gray area?
Like a lot of things, there's a little bit of a gray area. You can affect the crystallinity. So what happens is when you are cooling your part in the mold, it goes through a couple different thermal points. It goes starting at where it had been at, wherever we're molding it, whatever the temperature is, and then it hits what is called the crystallization temperature, the T sub C in your semi-crystalline materials. That's when you start to, the molecules are moving back into the crystal regions, and between that temperature and the TG that we kind of mentioned briefly, between those two temperatures is when you're going to start to recrystallize the material. So the longer that you can stay in that range and not go below the TG. So the TG specifically is where the molecules can no longer move if you cool under it. So if your TG, let's say, to make something up, is 100F, if you get under that, the molecules are no longer able to move. So the longer you can keep it between the two, the TC and the TG, the more it will crystallize. So that's why when you run a certain material, maybe you're running a nylon, maybe you're running, you know, whatever it may be, maybe it's a PPS, if you have it cool very quickly, the mold temperature is really low, so it cools super quick. It's not going to allow time for the molecules to get into back to their crystalline structure. So you're effectively going to be making an amorphous material out of a semi-crystalline material. And typically, the reason you pick those materials is because of their crystalline structure and what they give to that product and how it's going to perform. So if you take a Riton PPS material and you make it amorphous, it's not going to have the high, really excellent chemical resistance that it normally would. It's not going to have the high heat performance. And so essentially is you mess with the mold temperature and you allow it to stay within the range of the TC and TG long enough to crystallize effectively. We do know that, you know, the higher mold temperatures does mean that generally it's a longer cycle time because it has to stay in the cooling range long enough. But the idea is you're using that particular material because of the crystalline structures for a particular reason. So you don't want to not have those in your end product.
Yeah, I'd add to that slightly as well that, you know, as Andrea mentioned, it's really only pertinent for the most part in resin. And a lot of times the higher heat ones that we see increased crystallinity. You know, ABS and polycarbonate are going to reach a certain level of crystallinity, height or lack thereof, for a better word, because of the pendant group size in their polymer chains. So, you know, even if you expose them to more heat, it literally gets in its own way of becoming more crystalline. Where other materials like PPS is a good example, you know, it demands a really high mold temperature, and you know, a lot of shops either don't have the capabilities or don't want to run that high, but you will notice severe swings in physical property performance, mechanical performance, by using a hot tool versus one more akin to polycarbonate or nylon temperatures. Another question, Andrea, from Matt Copper. Are there additives for TPUs or TPEs or TPVs that can aid with release from the tool? And is there a specific texture you have found that can assist in release?
As far as additive, not ones that I've really seen that we recommend to help aid with it. It is more of a texture thing. They're very generally they're very tacky, and so you don't want a polished surface for your TPEs because they're going to want to stick. You want more of a textured finish, more of like an EDM finish maybe, because it will actually aid in release. It also, what is an added benefit is it tends to hide blemishes as well if you texture the mold, because they're pretty visible flow line problems with TPEs. If it's very polished, you'll see those pretty readily. So the texture not only will help with release, but it will also help with hiding those as well.
Yeah, to add to that, Matt, at times there are pre-formulated TPEs that may have slightly lower coefficients of friction. So not necessarily an additive, but we try to have, you know, our suppliers formulate for it ahead of time. There is one additive we use at times called siloxane, but it's basically a concentrate of a high molecular weight dispersed silicone within a pellet. With TPUs, TPEs, and TPVs, typically the problem with that is that it naturally adds to the surface hardness of the polymer, and therefore might take away from the softness that is, you know, the whole intent of using such a product to begin with. So if you have a specific, you know, type of product that you'd like it to add to or help with release, we have options. But to Andrea's point, you know, the tool texture is typically the best route. Plastics are improperly say they constrain the part that opened and they want to close it to retain that shape after annealing and release from the constraint.
I'm sorry, you're kind of cutting out a little bit, Jason. I didn't catch that.
Oh, sorry, I can rephrase it. Basically, they want to know if plastics are annealed properly, will they expect them to retain this same shape, even if it's constrained? You know, say they constrained an open part and they want to close it, will it be likely to retain that shape after annealing?
So the question would be, they are trying to fixture it while it's being annealed, and they want to know if it will still maintain that, or as if we just anneal it as a part, that it will not change shape. Is that kind of what I'm getting?
Yeah, a little bit of both.
Okay, so what will happen is, so the annealing, so we talked a little bit, if you got the answer for one of the previous questions, annealing essentially will increase the temperature of the product. It'll put it above its TG. So it can start to allow the molecules to move a little bit. So it'll allow it to start to crystallize a little bit as well. That's kind of the point for that. If you don't have the time to do it during your molding process and you have to shoot through the parts quickly and you don't allow them the time to crystallize properly, you can anneal them. It'll allow it to happen. It is likely to affect the dimensions a little bit because it's trying to crystallize. It's trying to shrink together into the crystal regions. So you are likely to see a change in that. I would imagine the fixturing of it would stop in those particular, wherever you're fixturing that particular dimension, be it maybe a hole or a certain length or something. If you are fixturing it to stop it from shrinking in that direction, I would expect it not to continue to shrink if it's being hindered. But overall, I would expect a shift, that it would change a little bit. I don't know the exacts. They probably have some studies for that, but it will change dimensions a little bit.
Another question related to annealing: do crystalline and amorphous products anneal similarly?
They're going to anneal a little different, and part of that is because the annealing process is to help with the crystallinity. So the products, the semi-crystallines that have a greater level of crystal regions, they're going to anneal. It'd be more effective for crystalline materials because the idea is to allow them to go back to those crystal regions. The amorphous materials, it's not to say that they don't have crystal regions, it's just if they do, it's not common. There's just small little areas. So you would be annealing those little portions that if they weren't already, got back to what you would consider maybe their happy place where they want to be in a nice crystal region, it will do that, but it's not as effective because the idea is to help allow those crystal regions to reform. And so it's more effective for your semi-crystallines.
Yeah, typically the upside benefit of annealing amorphous products will not actually help you gain that much in terms of mechanical performance, with the exception of if there happen to be molded in stresses in the part that would be, negatively affecting performance. It could help to release those. But as Andrea mentioned, it won't be able to affect the polymer formation, so to speak, or orientation tremendously, given just the size of the polymer chains within amorphous materials. Can PVC be annealed?
Can PVC be annealed?
Yeah.
You could, and similar to the answer we had for the last one, it would be more effective if there was molded in stress that we're trying to relieve. But as far as the crystal regions, PVC has a large pendant group, as Jason mentioned earlier, for some of the materials, so it doesn't allow it to form mini crystal regions, if very many at all. And so it would be more effective if you're trying to get rid of molded in stress, but not necessarily for the reformation of the crystal structures.
The other potential issue with PVC is that typically to anneal, you have to hold it at a relatively high temperature compared to whatever the thermal threshold is for that polymer. Many times that wane from a time perspective, and given the downsides of PVC and monomer, it would just be a tightrope to walk. I wouldn't say we have much experience with annealing PVC in particular, far from the experts in that. So certainly something to be cautious about. I believe that is all the questions. Thank you so much for your time, everyone. We really appreciate you spending your time with us to learn more about plastics and how we go through the material selection process. Andrea's contact information can be seen on the screen. Feel free to reach out with additional questions. Have a great rest of the week.